Today's topic is magnetostatics and we call it lecture 1a. In particular, we will be discussing in details what we mean by magnetic induction. Magnetostatics, as the name implies, it's a combination of two subwords. One is magneto, which means magnetic field, and statics, which means stationary. So magnetostatics actually is the study of stationary magnetic field. A stationary magnetic field is produced by steady current. Since magnetic field is stationary, the current that produces it has to be stationary. And current is produced due to a moving charge. Suppose we have a wire and there is transport of an elemental charge dq in elemental time dt, then the rate of transport of charge is dq by dt, which is I, and if I is constant, then we call it steady current, and the steady current produces a steady magnetic field. We can compare the situation with what you did in electrostatics, which is also a combination of two subwords. One is electro, which means electric field, and statics is stationary. So electrostatics is the study of stationary electric field, which is produced by a charge at rest. Say we have a charge q here, and in the region surrounding it we have its influence, and that influence is referred to as its electric field as per Coulomb's law. Now we have emphasized that a stationary magnetic field is produced by a steady current. Now, how do we know that? This follows from a famous experiment that was performed by a celebrated scientist whose name is Ørsted, and throughout our study we'll use Ørsted's approach. We'll adhere to Ørsted's approach. Now in Ørsted's experiment, there was a wire and a magnetic needle. If the wire did not carry any current, then the magnetic needle remained as it were. It refused to deflect. So there is no deflection. But if it carried a current, I non-zero means the wire is carrying some current, at once there is deflection of magnetic needle. The magnetic needle suffers an angular deflection. Now the magnetic needle responds to a magnetic field which was not there when I was 0, but definitely a magnetic field is created when we send I, and that is why the magnetic needle suffers a deflection. So this shows that this is actually experimental observation of the fact that stationary magnetic field is created by a steady current. So let us state again, steady current produces a stationary magnetic field, and we can rephrase it by noting that if the current happens to be non-steady, then the magnetic field associated with the current will also become non-stationary. So non-steady current produces non-stationary magnetic field. Let us now define certain characteristics of the magnetic field. That is, in other words, we'll try to describe what we mean by magnetic field. How will you, with what quantities will you define a magnetic field? Magnetic field is characterized by a quantity which is called magnetic induction vector, and it is denoted by B. It's a vector, and therefore we have an arrow sitting atop it. Let us consider a region of space where we have a charge q which is projected with a velocity v. This charge will move in a straight line. It will follow a linear path according to Newton's law. But if it so happens that this positive test charge q, which is fired with velocity v through this point P, experiences a sideways deflecting force vector F, then we'll say that in this region there is a magnetic induction vector B, because this magnetic induction B pulls this charge q from its linear path. This magnetic induction B being present in this region influences the charge q from following a linear path. It causes this charge to bend. The force that this B exerts on q is F, and this F is perpendicular to the velocity v, as well as it is perpendicular to the magnetic induction B. So in this description of magnetic field characterized by the magnetic induction vector B, we use 5 quantities: the charge itself, the velocity with which the charge has been projected, the magnetic field characterized by this magnetic induction vector, the influence of B on the charge q is F, and the angle which this B makes with V, which we call theta. Now, they are related by an equation which was first given by Lorentz and therefore is known as Lorentz force equation. So the Lorentz force equation is vector F equal to q into V cross B. Here cross represents cross product between V and B. Now this is the defining equation for magnetic induction vector. We also note that the force is perpendicular to velocity as well as magnetic induction. Force is perpendicular to B as well as vector V, as indicated by these relations. The dot product of V and F as well as dot product of B and F are 0, which can be derived from this equation very easily. So if you expand the Lorentz force equation, we end up with QVB sine theta, theta being the angle between V and B, and vector F is the bending direction. And it is clear from this relation that V, B and F form a right-handed triad. And very importantly, we cannot change the order of the vector quantities which are sitting in this equation. The vector F that appears in Lorentz force equation is called magnetic Lorentz force, because this F is created due to the magnetic induction. In this equation, if the quantities F, V and Q are measured, then one can easily find the value of magnetic induction. The electrostatic counterpart of this magnetic Lorentz force is nothing but Coulomb's law, which is F equal to Q into E. And this is the defining equation for B, the Lorentz force equation, and this is the defining equation for E. E is the electric field. The relation between force and electric field is that they are parallel, which follows from Coulomb's law. Q is a scalar, but here F is perpendicular to the magnetic induction B. Let us now define the magnetic field, which obviously is the region of space surrounding a current distribution. So the neighboring region of a current distribution is the site of a magnetic field, just as the region surrounding an electric charge at rest is the site of electric field. Next, let us define what we mean by B lines. The B lines are imaginary lines. They are drawn for convenience of depiction of B. To describe magnetic induction vector, to describe a magnetic field, we take help of certain imaginary lines. Now, the magnetic induction vector is a vector quantity, so it will have a magnitude, it will have a direction. Now this B line is such a line that at any point P, if we draw a tangent, it will indicate the direction of the magnetic induction at that point. And if we consider the B lines, and in these B lines, let us consider an area. So number of B lines in a region gives the strength of B. So here, for instance, the area, through the area, there are 5 lines intersecting through it, while here there is only one line. This is indicative of the fact that in this region, the strength of B is large. The value of B is large, while the value of B is small here. Here, it is a low B case because of scarcity of lines. B lines are sparse here, while there is crowding of lines here. Too many lines in this region indicates that the value of magnetic induction is large at this region. Let us move over to Lorentz force again. Let us consider a region of space where a charge q is considered, and suppose the charge is moving with velocity v. Now at any point, the charge is acted upon by an electric field and also magnetic field. So the total force that this charge, which is in this field where E and B are active, experiences will have two parts. One is Q into E, which is the Coulomb part, which tries to push the charge forward, that is, forward means along E, and the other part or portion of F corresponds to the magnetic force part, magnetic Lorentz force part. Here E tries to push Q forward, but B tries to bend the charge, deflect it sideways, as we mentioned before. So this is the Lorentz force. Lorentz force has two parts. One is the Coulomb part, the other one is the magnetic Lorentz force part. Let us now discuss a bit about the dimension of B, and then we will discuss the dimension of unit of B. Let us recall the magnetic Lorentz force equation, which is vector F equal to Q into V cross B, from which we can write B is of the order of F by QV. This is, mind it, a crude form. This is not a definition of B. The definition of B follows from Lorentz force equation. But just to get a rough estimate, to get an estimate of the dimension, the unit of B, we write B in this way. Now, substituting the dimension of force, dimension of Q, which is Coulomb, and dimension of V, and simplifying we end up with this expression, which can further be simplified if we note that I is dq dt. Then we end up with this relation. Here m is mass, that is kg, L is the dimension of length, and T is dimension of time, which is actually represented by the unit second, and C here represents Coulomb, and A here stands for ampere. And this is how ampere and Coulomb are related, which directly follows from I equal to dq dt. So having got the dimension of B, let us move on to finding the unit of B. Unit of B in the SI system is defined as Tesla, and in Gaussian system it is Gauss. Now let us, from the magnetic Lorentz force equation, write in a crude way, just to get an estimate. B is equal to F by qv, and instead of V, which is velocity, velocity is length by time, we get q by t, and q by t is actually I, so here we have I, and therefore this yields B equal to F by IL. So now it is time to substitute the units. So instead of B, let us write Tesla, instead of F we have Newton, instead of I we have ampere, and instead of L we have meter. So this combination of units, Newton per ampere per meter, is defined as Tesla, which happens to be the unit of B. In a similar way, in the Gaussian system, instead of Newton we will have dyne, instead of meter we will have centimeter, and instead of ampere we will have the electromagnetic unit of current, which is ampere. And this combination of units is known as, or stands for, what we call Gauss, which is the Gaussian unit of B. There is another popular way to write Tesla as well as Gauss, and that follows from, this alternate popular form follows from the expression of energy. Energy can be written as power into time, and power is I into V. I current, V is potential difference or potential, whatever. Also energy is work, and work can be written as force into distance. So energy has two expressions which can be equated, and simplification gives us B equal to F by IL. From here simplification gives us F equal to IVT, which if we put in this equation B equal to F by IL, we end up with B equal to Vt by L square. So two important expressions are there. One is B equal to F by IL, which we used here, and another equivalent expression of B we have derived, and that is B equal to Vt by L square. And now it is time to write down the units again as we did before. So instead of B, let us write Tesla. Instead of V, we'll write volt, and time will be replaced by second. L square is meter square, so volt second per meter square. This combination of units is what we call Tesla. So Tesla can be defined in two ways, either this combination or this combination. Both correspond to Tesla. In case of Gauss, which is the unit of B, we have substituted ab volt instead of V. Ab volt is the electromagnetic unit of potential difference, and therefore ab volt second by centimeter square, this combination gives us Gauss. So the unit of B is Tesla in SI system and Gauss in Gaussian system, and they must be related. So now let us try to obtain the relation between Tesla and Gauss. 1 Tesla is this combination volt second per meter square, which we got here, and we'll now use the interrelation or conversion factor. So instead of 1 volt, let us put 10 to the power 8 amp volt as per the interrelation between SI unit of potential or potential difference and EMU, electromagnetic unit of potential or potential difference. So instead of volt, 1 volt, we'll put 10 to the power 8 amp volt. Second is same in both systems, and meter is obviously replaced by 100 centimeter, and simplification gives us 1 Tesla is 10 to the power 4 Gauss. And we just note that, though we are not using it, 1 volt happens to be 1 by 300 stat volt. Volt is the SI unit of potential difference, and the ESU unit or the electrostatic unit of potential is stat volt, while the electromagnetic unit of potential is amp volt. We next try to interrelate E and B in terms of their dimensions, or the Lorentz force relation, which written in a crude form gives us B of the order of F by QV. From here also we can find how are they related. So B is F by QV, and we can write F by Q in the numerator. Denominator contains just V, and we know by Coulomb's law F by Q is E. So instead of F by Q we have E. So B is E by V, which directly gives us E by B is of the order of V. So the ratio of electric field and magnetic field is actually a velocity. And from a different subject, electromagnetic theory, we know that these fields, they propagate at the speed of light. So this V is actually the speed of light in free space, whose value is 3 into 10 to the power 8 meter per second. We can rederive this relation from dimensional analysis. When we put E's, we replace E by its dimension, B by its dimension, take a ratio to end up with the same result, L by T is V. And the dimension of E follows from Coulomb's law. We replace F by its dimension, Q by the Coulomb, and simplify it to end up with this dimension. So we get the same result in both cases, and we have to get it. We'll now define magnetic flux. Magnetic flux represents the surface integral of B over S. So if we have a surface S in a region where there are B lines, where there is a magnetic field, so this is a region where we have B lines which characterize the magnetic field, and this is the direction of B, say. So we have considered a point P on the surface S, and at this point P, the B line, the tangent to the B line is this one. So this is the direction of B at P, and through P we can imagine an elemental surface ds, and n cap is the normal unit vector. So vector B dot n cap ds, vector ds is n cap ds. So if you take dot product of B and ds and consider all such ds's, this is just one ds shown, and there are innumerable number of ds's here, which when combined we get s. So you just sum it, then we end up with the magnetic flux. So magnetic flux is the surface integral of magnetic induction vector across or over a surface S. So next is dimension of the magnetic flux. Magnetic flux, if it is written in this way, then it follows that phi m is B into area. Area is L square, so phi m we can write as BL square, just again crude way of writing it. This is the actual relation. So to get the dimension you can write in this way, and you replace B by its dimension. This is what we got earlier, and L square is here, so you simplify it using I equal to dq dt, which leads to the relation between Coulomb and Ampere. That gives us this dimension of magnetic flux. And next, the unit of magnetic flux. Magnetic flux can be written as B into L square, which means the SI unit is Tesla for B and meter square for L square. So it is Tesla into meter square, and this combination of units is referred to as Weber, which happens to be the SI unit of magnetic flux. The Gaussian unit of magnetic flux is similarly found to be Gauss, which is the Gaussian unit of magnetic flux multiplied by the unit of area, which is centimeter square in Gaussian system. So Gauss centimeter square, this combination of units is referred to as Maxwell. So Weber is the SI unit, Maxwell is the Gaussian unit of magnetic flux, and since Tesla and Gauss are related, as 1 Tesla is 10 to the power 4 Gauss, we can easily interrelate Weber and Maxwell, and that has been done in this section. So how many Maxwell is 1 Weber? So start from 1 Weber equal to 1 Tesla into meter square. Instead of Tesla, we'll put 10 to the power 4 Gauss and convert meter to centimeter, and then simplify to get 10 to the power 8 Maxwell. So 1 Weber is 10 to the power 8 Maxwell. Now we use various abbreviations for these quantities, and they are listed over there. We, instead of Tesla, to save time and space, we use capital T. For Gauss we will use capital G. For Weber we will use capital W small b, and for Maxwell we will write in this way, capital M small x. So these are the abbreviations that are used. So let us now wind up our discussion. Let us make a gist of what we did over the course of time. Q, the charge, if it is static, if it is at rest, it creates an electric field, while if it is in motion, it produces a current, and that current produces a magnetic field. This electric field is defined from Coulomb's law, and this magnetic field is defined from Lorentz force. So E is defined from Coulomb's law, F equal to Q into E, and the defining relation for B is given by Lorentz. And here Oersted, we have two experiments. Coulomb did experiments to find the Coulomb's law, and from Oersted's experiment we end up with this relation. So this is actually Oersted's observation that some I produces a B, and that is why the magnetic needle deflected. E and B both are vector quantities, so we can write them in this way. They have a magnitude part, they have a direction part. The dimensions were obtained. Here the dimensions also can be written in this way, converting them to units, and this combination of units is actually Newton per Coulomb for electric field, and for magnetic field we have Tesla, which is actually this combination. We also did E by B, and E by V turned out to be C. The magnetic flux, the expression of which we defined in this way, whose SI unit was Weber and the dimension was this combination of units. And lastly, we interrelated SI units of magnetic induction and magnetic flux to the corresponding quantities in the Gaussian system. So 1 Tesla is 10 to the power 4 Gauss and 1 Weber is 10 to the power 8 Maxwell. So in the discussion that we made, we came across the name of a number of scientists, celebrated people, and we can list them. They are Coulomb, they are Oersted, Lorentz, Ampere, Gauss, Tesla, Maxwell, Weber. We discussed a volt, somewhere we used volt, and that volt follows from volta. And of course we have Newton, the ubiquitous person. In any discussion regarding physics, we have to mention his name. So in the next lecture, which will be a complementary one to this 1A, we can discuss about these scientists, a bit of their contributions, just to show respect to these great people. You might have queries, you might point out some anomalies, or presentations may appear to be improper to you. Then we can address those things in this lecture 1B, and also we'll discuss certain problems in 1B. I'll wind up this discussion following the words of Jane Mansfield, who was a Hollywood actress, and according to her, I will never be satisfied. Life is one constant search for betterment. So let's hope the next video, if I am able to prepare it, will be better than this one. Thank you.